Now, we're moving on to looking at DC circuits themselves. We've talked about current, and we've talked about capacitors and electric field. Here we're going to talk about the circuits. And just for good measure, here is the robot from the movie Short Circuit. So, we talked about current already, but just as a bit of a recap, the current I is defined as the amount of charge that passes by a point in a circuit per unit time, or I equals Q over T. The other governing equation for our circuits is Ohm's law, V equals IR, which can be rearranged to give us R or I for our circuit. Now, when we define a circuit, what we're actually talking about is closed loops of conductive material, be they wires, as they are in this crude diagram here with a battery hooked up to a lamp and a switch, or more modern systems tend to use these sort of printed circuit boards. They're still conductive pathways, and they still carry electrons from one component to the next. Here are the capacitors, and here's the chips in this particular board. And you can put resistors, capacitors, diodes, or whatever electrical components you wish into your conductive pathway to control the flow of electrons. So the systems that we're talking about here are DC circuits. That means direct current. That means the current is moving one way and is not fluctuating in our circuit. And things like batteries give out one-way DC electricity. We'll talk about AC electricity a little bit later once we've talked about magnetic induction. But batteries give out an electromotive force, and this is given as an EMF, or this little epsilon here. And an EMF is what produces our potential difference from a battery. Now, the difference between a battery and a capacitor, as we've said before, is a battery replenishes its potential difference, which means it's an electromotive force. A capacitor has a potential difference the same as a battery, but it doesn't actually have an electromotive force. And that means an electromotive force is really a voltage. And that voltage is across the terminals of the battery as the negative charge is moved to the positive side of the battery. So delta V, the voltage you'll get from your battery, is the electromotive force minus the current times a tiny little resistance. So if V equals IR, you can see this is actually a voltage. It's a difference in voltage across the battery. So this is how much voltage you should get out of your battery, and this is how much voltage you actually get out. So this tiny little resistance takes some voltage away from your system. So if you buy a 9-volt battery, you're probably being a little short-changed and not getting 9 volts out of it. You're probably getting 8.98 or 8.99 or something like that because of this equation. So in terms of batteries in circuits, we can say delta V for our battery is our electromotive force minus IR. Both of these will come out in volts. We can sub in V equals IR, of course, and have voltage on both sides. This is I times the resistance of the circuit, whereas this is I times the internal resistance of the battery. So the current supplied by a battery becomes I equals V for the electromotive force divided by the total resistance of the circuit. And that total resistance is R for the circuit plus R for the battery. Now bear in mind there's a reason this is a little r, this is the internal resistance of the battery, and it's often quite a small number compared to this one. So the EMF here is the work done per unit charge produced by your battery. And so the units of EMF are volts. So EMF minus I times R. Let's take a look at a quick example. So a battery here is rated at 1300 milliamp hours. Okay. How many electrons can this battery supply? And we've talked about amp hours a little bit before. So we've got 1300 milliamp hours. That means this is 1.3 amp hours. So what's going to happen with this is we're going to hook up this battery and it's going to pull current out of it. So electrons are going to be drawn from that battery until 1.3 amp hours of electrons have been pulled out. So we can say delta Q, the amount of charge coming out of the battery, is I times T. This is going to be 1.3 times 3600 seconds. That's 60 times 60. This is 60 minutes, 60 seconds. That's going to be 4,680 coulombs delivered in total. So now we can say N is equal to how much charge has passed. So N is essentially going to be our charge divided by that of the electron. So delta Q over the electron's charge. So 4,680 coulombs over 1.6 times 10 to the minus 19 coulombs per electron. So that'll give us 2.95 times 10 to the 22 electrons. So let's take a look at a slightly different one. Now we've got a battery that has an EMF of 2 volts and delivers a current of 0.84 amps for 154 seconds. So the units here are a little nicer to play with. What is the charge that passes through the circuit? Well, we know how much current we have. We have 0.84 amps of current, and we know we have 154 seconds. So no conversion is necessary here. Delta Q is I delta T. 0.84 by 154, that'll give us 1,322.16 coulombs. But what is the work done by the battery? Well, the work done by the battery will be how much charge has been moved multiplied by voltage, or work, the energy, will be Q times V. Q here is the 1,322.16 we found in part A. Our voltage is 2 volts, which means we'll multiply that by 2 and get 2,644.32 joules. So that's batteries. Let's move on to talking about one of the last electrical components we'll actually introduce, which is a resistor. A resistor, as we've already kind of discussed a little bit, is an object that has some resistance to the flow of electricity through it. And even wire has some specific resistance, but when we choose wire for our conducting pathways, we try to choose a wire which is low resistance, which likes the electrons to move through it, so we don't have to worry about losing power in a circuit just by the wires themselves. And we can control that using these resistors. So if we take these objects and we consider them to be like water pipes, then a resistor is really a narrowing of the water pipe, causing a bit more pressure, but also causing resistance to the flow of our current. And these are really useful because we can use them to regulate voltage and regulate current. If we look at the equation V equals IR and the other equation P equals VI, we can actually see that we can change the power and we can change the voltage and the current, all of those things interrelated, by moving the resistance. And when we look at resistors, here's some typical resistors, and you can see here are the colors of each one, and they've got some colors with different bands, different colored bands on them. And these resistors all have an actual chart which tells you what these little colors represent. This isn't just to make circuits pretty. These colors all represent numbers and tolerances for our specific resistors. Now that's more of an electrical engineering task and something you would see in a lab, but you can follow that chart and you could figure out the specific resistances here, and you could put the right ones into your circuit and using various combinations come to the resistance that you want, which is what we're going to study here. So before we proceed with our networks of resistors, there are two basic types of circuit that we have to consider. There is a series circuit, which allows a single path for our electrons to flow through, and what we call a parallel circuit, which, as it sounds, provides two or more pathways for our electrons to flow through. And circuits can be either one or the other of these, or a combination of these types. So here on the left is an example of a series circuit, and here is a parallel circuit. For a series circuit, the electrons must flow through every component in the pathway. The electrons are coming out of this battery here, and these X's are actually bulbs in this case. So the battery is providing current, and the current is going through each and every device in this circuit. In a parallel case, the current is still going through the devices, but it has multiple pathways, and the electricity will split based on the path of least resistance. The path with the least resistance will get the most current. So the electricity will move along here, reach this junction and split two ways, reach this junction and split again, and then reach this junction and travel through here. So there's our series circuit, and there is our electron moving through this resistor and then subsequently moving through this bulb, and the electron will continue to move through this circuit until the battery runs down, runs out of power, and no more electrons can go through. But as it goes, it will experience resistance as it moves through this resistor, for that is what they do, and then it will experience a resistance as it moves through this bulb and causes it to light. So for our electrical system here, for our circuit, we have a single path for all our current to flow through. And you've seen similar rules for adding resistances as you have for adding capacitors, but the rules are flipped, so please don't mix them up. So if we're to find the total resistance of a series circuit, all we really have to do is add our resistances together. So the effective resistance here is the sum of all the resistors in the series. So the total resistance of this circuit will be R1 plus R2 plus R3 plus R4 blah 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 for however many resistors you have. You can also look at how the voltage is split between those resistors and sum those together too. So let's take a look at a quick example here. Here we've got a current and it's going to move through this particular system, and it's only got one path that it can move through here. 10-volt battery here, a 5, a 3 and a 2. The sum across these potential differences will equal the potential difference across the battery. So we don't know what these resistances are here, but if this is a 10-volt battery, we'll end up with a total of 10 volts across these resistors in terms of potential difference. In terms of resistance, here is our battery, and here's three resistors, a 15, a 10, and a 6 ohm. So here we've got a 10-volt battery. The total voltage through this circuit is 10 volts. And what we're going to say is, what is the resistance? Well, as we said, our total here is 15 plus 10 plus 6. So our total becomes 31 ohms. If we want to calculate the total current, as the question asks, we now have to say I is V over R total for this circuit. So we have just found that there's 31 ohms of resistance and our voltage is 10 volts. So 10 volts over 31 ohms will give us about 0.3199, something like that, amps, or 0.32 amps. So in our series case, we have our current moving through the circuit, and the same current will be flowing through every part of our circuit. So here's the situation. Our current is coming out of the battery, traveling through each of these bulbs and lighting both of them. Any electrical circuit that provides a single path for our current is going to be delivering a power of P equals VI, where V can be found from IR, of course. This means if you add more resistors in a series circuit, so if we keep putting light bulbs and stringing them together in our circuit in series, what we'll do is just keep adding to the resistance, R1 plus R2 plus R3 for however many resistances we add. And that will cause the total resistance to go up. as all the current has to travel through each resistor in turn. Consequently, the current in the circuit will go down and the lights will dim as more resistance gets added. So the more lights you add to a string of battery, if you take a battery and add a string of lights and keep adding lights, eventually all those lights will just become dimmer. Take a couple of those resistance sources out, i.e. take a couple of the bulbs out and then reconnect the wires, of course, and they'll all be brighter. So essentially what you're doing is giving the same current, delivering the same amount of power from the battery to all three bulbs. So the power is divided amongst these bulbs and they all become dimmer. And this is the kind of thing you often get with Christmas tree lights. They're a series circuit, and they're not so bad now as there are ways and means around this, and these things have gotten more complicated as we put things like chips into the actual systems. But there was a time where if your Christmas tree lights went out, it meant one of those bulbs was defective. And that meant you had to go all the way through and find out which of those bulbs it was and get your Christmas tree relit. Consequently, 240 fires or so a year are actually caused by faulty Christmas tree bulbs. That's an actual statistic, not just making that one up. So that really identifies a serious disadvantage to a series circuit, and that is if you remove any device from the line, then all the others will cease to function. So here Luigi smashes this particular bulb and all the others will go out because you've broken the electrical connection. And as we know, bulbs occasionally stop functioning. Now where a parallel circuit is concerned, our electrons can split and travel down two separate pathways, or more than that. Here just two. So the electrical circuit that's known as parallel provides more than one path for the electrical current to follow. So the total current in the circuit is the sum of all the current in its paths, or branches, either term. But the resistance now, if we're to add all the individual resistances, is given as an inverse. So 1 over R total is 1 over R1 plus 1 over R2, 1 over R3, blah, 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 for however many resistors you have. Common error here, very common error, is that if you do 1 over R1 plus 1 over R2, people often forget that that total is also inverted. So you invert your resistance, add it to another inverse resistance, and then invert the total. Quite often, people forget to invert the total. And it actually gives quite a reasonable value, so people often miss that. Don't be one of those people. So, as we've said, electricity likes to follow the path of least resistance, and earlier on we talked quite a bit about lightning, and that's why you get this crackling pattern here, as lightning is just electrical current and it's following the path of least resistance. So it's following the moisture in the air, it's following the most conductive pathway, and this is a really great picture because you can see the discharge occur here. But just like lightning, if we put electricity through a circuit, more current will follow the path of least resistance. The smallest resistor will get the greatest current moving through it. So that means the smallest resistor gets more current passing, the larger resistor gets the least current passing through it. So let's take a look at a parallel example. So for resistors in parallel, if we wanted to find the total resistance for this circuit, we'd have to add our 30, 60, 20 and 10 ohm resistors here that are constructed in parallel. So here's our battery, the electricity will come in here and split four ways proportionally to the resistances here. And that means 1 over the total resistance will be 1 over 30 plus 1 over 60 plus 1 over 20 plus 1 over 10. Now, I realize that In the old days, in days gone by, people would cross multiply this and do the calculation, but you can just do the inverse on your calculator. Invert the 30, invert the 60, the 20 and the 10, add them up, and then invert the total. It's a lot faster than doing this. But if you do cross multiply and do the calculation, this is what you'd get: 2 60ths, 1 60th, 3 60th, 6 60th. But 1 over r will give you 1/5. So that 1/5 is actually quite a reasonable value as a number. Some of the calculations we've done will give you answers like 10 to the 3 if you get them wrong, for instance. But 1 over 5 is 0.2, which doesn't seem like a terrible value, but that 0.2 would be wrong. So 1/5 or 0.2, you now have to invert that. So this will become 1 over 1 over 5 or 1 over 0.2, and that will give you 5 ohms. So even though we have here 30, a 60, a 20, and a 10, 60, 70, 80, 90, 130 ohms or so of resistance, we only get 5 ohms in total once we have split our resistances up in this fashion. So you have to use the inverse rule for parallel resistances. And of course, this is just the old way of doing it. You can ignore this page number. So I would say just do this on your calculator, add them up, make sure you invert your answer. But of course, even then, the reciprocal sum rule can get pretty complicated for large numbers of resistors. We probably won't attempt systems like that for more than like 5 or 6 resistors in our particular case, now that we're using calculators. And this cross multiplication can be done should you not have a calculator handy.